This is Statistics 243 at Berkeley for Monday, October 27th. Okay, let's go ahead and get started. So I put up here, this is from the Gentle book that's referenced in the syllabus, and I thought what I'd do, we'll come back and see this, I'll put it up next time as well. It's just meant to sort of give a listing of some of the common factorizations of matrices, many of which we'll talk about in some detail. Just to give you a sense for why we're covering these, the SVD is often used in statistical modeling, including in machine learning, serves as a way to decompose variation into different features. We're going to see that we often will use the LU decomposition as a way of inverting matrices and or solving systems of linear equations. We're going to see that we'll use the QR decomposition to run regressions, and that's the standard way to actually fit a regression, is to do this QR decomposition and then do some additional manipulations. We'll see that we often end up working with Cholesky decompositions if we're thinking about, say, multivariate normal distributions and we want to generate a random vector that has the covariance equal to some covariance matrix. There's a way to do that with a Cholesky decomposition. And then eigendecomposition and getting eigenvalues and eigenvectors is, of course, comes up a lot in doing principal components and those sorts of operations. And there are tons and tons of variations on principal components analysis that, at their heart, have something like this lying underneath them. So that was the goal there, was just to give you a general sense of where we're going. And this says what the properties, so this says what the decomposition would look like in a particular notation. And this says what are the properties of these matrices that are the decomposition of the A matrix, which is the input. And they're often either going to be orthogonal matrices, diagonal matrices, triangular matrices, where you have either zeros on the upper triangle above the diagonal or zeros on the lower triangle of the matrix below the diagonal. So that's what I mean by upper triangular and lower triangular here. And once you get these decompositions, the fact that they have some of these properties often makes them quite easy to work with, or either easy to work with numerically and computationally, or they have a nice interpretation once you've gotten them down to this form where you've done the factorization. Okay, so let's pick up on one of these. I want to go back a little bit to where we were talking about positive definite matrices, and I want to relate that to the eigendecomposition, to eigenvalues and eigenvectors. And this may be a little bit of a different perspective on it than what you would have seen in a linear algebra class, because I want to think about it from a sort of statistical perspective of what one way of interpreting the eigenvalues and the eigenvectors. Okay, so what I've done here is assuming that if we have a symmetric matrix, then gamma is going to be orthogonal, so I can write the inverse on the right-hand side as gamma transpose. And in fact, if we have a positive definite matrix, then the result of that is the diagonal elements that are in this lambda matrix. This is going to be a diagonal matrix. The diagonal elements are all going to be positive. So one way to think about this is if I start with this and I say I'm going to start with some z's that are independent of each other, they're uncorrelated. And I take the square roots of the eigenvalues, so this is a matrix with zeros here, and multiply that by z, and then I multiply by the matrix of eigenvectors, which are the columns of this matrix. That is one way to generate a vector of y's whose covariance is going to be equal to A. So you should be able to show that very easily. But now let's look at what are the pieces that go into this in terms of what we're generating. We can think of this as, well, if we're multiplying the z's, the vector of z's by this diagonal matrix, all we're doing is we're saying that there's some z star that is equal to, let's see how do I want to write this? Well, maybe I'll write it with indices. So we have zi star, and that's just that's lambda I to the 1/2 times the original zi. And now, if I want to generate y, what do? Well, then I get that y is equal to gamma dot I times the zi star. So let's think about what that means to be able to interpret that. We're basically just taking linear combinations of the eigenvectors. We're just taking linear combinations of the columns of this matrix, which are the eigenvectors of this matrix, of the original matrix A. So this is just a linear combination, a weighted average of those columns of the eigenvector matrix. So you can just think of these as being features or patterns. We have different features that we're weighting differentially. And when we weight those differentially, that's going to give us this vector y, where we started with just, we can think of the z's as being sort of, we can think of them as being random weights. So a simple example here would be, let's take z to be normally distributed, mean 0, and variance the identity matrix, covariance matrix the identity matrix. So just a set of independent scalar normal, standard normal random variables. So these are random weights. These are patterns. And the lambdas are scalings. Those are standard deviations, or square roots of variances. So usually when we write this out, we're going to write these in decreasing order. So this is going to be the biggest value, this is going to be the second biggest value, this is going to be the third biggest value. So you can just think of this as the eigenvalues are the variances of these random weights that are then applied to the patterns, the eigenvectors. So the square roots of these are the standard deviations that are used for the random weights. So to me, this is how, when I think about eigenvalues and eigenvectors, I usually think about it this way, because this is usually a useful way for me to think about it if I'm thinking about a statistical problem, as opposed to sort of thinking about an abstract linear algebra situation. Okay, are there any questions so far? The other thing that you can think about here is, as we get down here, often these are going to be fairly small values on the lower part of this diagonal. So these are going to be the less important, these are going to be the smaller eigenvalues, which means they're going to be smaller values that get multiplied by the small values that get multiplied by the z stars. Small values that get multiplied by the z's. So if these are small, z star is small, and that means we just have a small weight on this particular eigenvector, this particular pattern. So that's an eigenvector that's not represented with very much magnitude in the resulting y vector here, so it's not very important. So if you wanted to come up with a reduced, if you wanted to come up with a representation of y that was basically an approximation, you could do that by basically just truncating this at some point and throwing away all of the eigenvalue-eigenvector pairs where the eigenvalues are small. And the y that you got from just using the first few eigenvectors and their corresponding eigenvalues would be, I don't know, y tilde. And y tilde and y might be fairly close together if the ones that you threw out had small eigenvalues. Because those don't contribute much in terms of the weights in this linear combination that goes into making up y. So there are going to be cases where, for example, numerically, we might end up with doing an eigendecomposition, trying to compute these eigenvalues, and we might end up with an eigenvalue that, even though we know the matrix is positive definite mathematically, when we do it on a computer, we might end up with a value here that's negative. And the reason for that is the numerical inaccuracy that we've talked about in Unit 7. But the ones that are going to be, the numerical accuracy is really going to be most affecting the smallest values, because if you have a little bit of inaccuracy here, and this is a value of 1 or 10 or 100, maybe that probably doesn't matter too much. But if you have a value here that's 1 times 10 to the minus 12, and then you have some inaccuracy, and that ends up being minus 3 times 10 to the minus 15, Well, then you can't take the square root of the negative number to do this, to make this representation. But suppose I did have a value in here that numerically, once I did this as a computation on the computer, I had minus 3 times 10 to the minus 15. And suppose that I just arbitrarily said, oh, I'm just going to set that equal to 0 because it's going to give me problems if I try and take a square root here. Is that something we should be concerned about from this perspective of weighted averages?
Part of me says yes, part of me says no.
Okay, so why on both sides?
So the no in that it's not going to affect the weighting so much because they're small to begin with, so 0 is approximately close to small.
Yep.
But then it will be a problem in that 0 is not small, and so you're going to get some skew because of that potentially.
Okay, so yeah, so what do you mean by skew? Just difference from the truth? Or?
Yeah.
Okay. Yeah, so I mean, it's true that you'll get something that's different than you would have gotten if you could actually mathematically do this decomposition and get the true eigenvalues along here. But going back to your first point, which I think is, in this case, to me, the more salient one, is that if we're thinking of this as the weighted average, let's suppose this is n by n, and so I have lambda n is truly 1 times 10 to the minus 12, and the other lambdas are much bigger, 1 or 10 or 0.03 or something like that. Whatever my z is, it's going to be something between, say, minus 2 and 2, roughly, because if it's just a standard normal, for example, and if I put a distributional assumption on the z's. Well, now if I just think of, now I've got this very small number multiplied by a z that's between, say, minus 2 and 2. So this is basically going to zero out this z star compared to the other patterns. So if I go ahead and just set it to 0 because of the numerical problem, that's really not going to be much of a concern in the resulting y that I get, because this y wasn't going to be very affected from the very beginning by this last of the eigenvectors. And that is a fairly standard thing that we might do, is do this sort of truncation. Okay, questions about that, comments? Let's see what else I want to say here. Okay, so the other thing I wanted to mention here, which is in these sort of bullet points down here, is if we had a positive semi-definite matrix, then what that means is that one or more of these eigenvalues here is actually exactly equal to 0. So what's going to happen then? Well, sort of the obvious thing, that 0 is just going to end up zeroing out the contribution of whichever eigenvector it's associated with. So that eigenvector pattern doesn't contribute anything to the variation in the y vector. So basically, if you have 0 eigenvalues and you have a positive semi-definite matrix instead of a positive definite matrix, instead of having a set of n features that we're using, n different eigenvectors, we have however many fewer eigenvectors that we're actually making use of, as there are 0 eigenvalues. So it's basically just a lower rank, this y can be represented in a lower rank representation than could a y than would a y where we had all of the eigenvalues being non-zero. There are just fewer. There are either more or fewer patterns being used to construct the y, depending on whether some of these guys get zeroed out. Yeah. Another way of saying that is just if you've got some 0 eigenvalues, then y is living in a lower dimensional space than y would be living in if all of the eigenvalues were non-zero, bigger than 0. Okay, the other thing I wanted to mention was the idea of a generalized inverse here. Okay, so all of you, I think, have probably seen generalized inverses. They have this representation here where we have this notation for the generalized inverse. There's a particular generalized inverse called the Moore-Penrose inverse, which is also called the pseudo-inverse. That's often denoted A+, although not all the time. And it has this definition here. So what I wanted to just comment on here is basically what's going on if we use a generalized inverse, in particular the pseudo-inverse. So let me see if maybe I'll try and reach up here and see if I can do this while keeping this existing. So suppose I have a matrix Q, and instead of, I was thinking of this as being a covariance matrix. Suppose Q is the inverse of A. So Q is what's called a precision matrix. Sort of makes sense if you think of the inverse of the variant. The variances tell you how uncertain you are about things. If you take the inverse of a variance, 1 over the variance, it's a precision. That tells you how certain you are about some random quantity. So if I represented that as gamma, and I'm going to call this lambda inverse, gamma inverse, because we're going to come back to the covariance matrix. Then in this gamma inverse matrix, suppose this matrix had what was this? I guess I'll put it down here. Suppose this inverse has some eigenvalues, and then it has an infinity here. What does that say? That says that we have basically infinite precision for we have infinite precision. We sort of know exactly what this sort of random representation sort of means. We sort of know exactly what one of the components of variation is. Let's see. Oh, sorry. I'm getting myself turned around here. I want to start out with a 0 here. Okay, so that makes more sense. So I want to start with a 0 here. So I have 0 precision, which if I then took the inverse of this, means I have infinite variance, or sort of no information about that component of the problem. So now if I try and go from A inverse back to A by taking the inverse of A inverse, the way I can do that when I have an eigendecomposition is just take the inverse of the diagonal matrix that's sandwiched between the eigenvector matrix and its transpose. So if I try and do that, what am I going to get? I'm going to get gamma times a matrix that these are, suppose these are not 0, so I just take 1 over them, and that will give me the values here. But now I have a problem. I'm trying to do 1 over 0, and that's going to give me infinity. So now if I started with this matrix, I tried to get to A, and I tried to use this in my constructive formulation of constructing this Y by weighting these different patterns that are the eigenvectors, I'm going to have a problem because I basically have infinite variance on one of the eigenvector patterns. And so I can't generate from something with an infinite variance. So the standard solution in this sort of situation is to use a generalized inverse, which basically corresponds to taking these places where I would get an infinity and converting it to gamma, the same things here as I had over there, but sticking in a 0 here. Okay. So in some ways this looks crazy, right? You're starting out with something that's really big and you're sort of going all the way in the other direction and setting it to be 0 as your solution to the problem. Right? So that seems like the exact opposite of coming up with solving this problem that I have an infinity here. But in another sense, it sort of makes sense because I basically say, well, I can't generate, there's so much uncertainty in that component that sort of the only way I can deal with it is basically to throw that component away. We've already sort of gone through the logic of if I put a 0 in here, I'm basically putting 0 weight on that eigenvector component in that pattern. So in this case, what am I doing? Well, I'm saying, well, I don't know how to deal with this, so I'm going to work with this constrained representation where I'm going to say there's no contribution coming from that, say in this case, that last eigenvector. And so one way of thinking about these generalized inverses is that I'm introducing a constraint here. So I'm now going back to this idea that I'm in this lower dimensional space. I'm not accounting for the variation in one of the dimensions because I just don't know how to deal with it because there was no information about that dimension. And so I'm going to work with a constrained formulation in this situation. So I wanted to go through that to sort of relate this idea of, you guys have probably seen generalized inverses from sort of a linear algebra perspective, but again, this idea that when I think about generalized inverses, I often usually think about it in this way, and I think about the fact that we must be imposing a constraint somehow on the problem by doing this sort of operation. And we're working in a reduced dimension space. Another sort of framing of this is we have an underdetermined part of the system, and so we're going to impose a constraint to deal with that lack of determination in one of the components. Let's see. I think I have an example here that I think I'll let you guys read through on your own rather than working through, and I have some code that goes along with this example. So if you're interested in this, this would be useful to check out, and I'm happy to answer your questions outside of class as well. But they're basically, if you have this kind of, if you have a model like this, which is basically a sort of random walk model, you can basically write that model down with a precision matrix that looks like this, where the diagonals are 2s, and there are some -1s on the off diagonal, and then there's a 1 up here and a 1 up here. So it's all 2s in the diagonal, there's a 1 here and a 1 here. This matrix corresponds to this matrix Q, and you have to do this sort of constraining business to deal with these kinds of, in some cases, usually to deal with these kinds of models. And then I have an example here of actually doing that in R, working with the eigenvectors and eigenvalues. And I guess I'll just mention while I'm on that if you want to get an eigendecomposition, get the eigenvectors and the eigenvalues in R, you just call the eigenfunction, and then what you get out as the values element of this list object that comes out is just the eigenvalues in decreasing order, and you get out a matrix as $$ vectors, and if you just pull off the columns, those are the eigenvectors for the original matrix, which in this case was this matrix I called precision matrix. All right. Okay, questions or comments before I move along? Okay, so the next bit I'll talk a little bit about is just sort of starting to talk about computational issues that come up in working with matrices and trying to relate some of what I've been talking about, which is sort of more statistical or mathematical, back to computational questions. So one of the things I want you guys to have in mind when you're thinking about a lot of what we're going to talk about is optimizing the speed of doing these linear algebra calculations is there are sort of 3 different ways to get good speed in doing these kinds of things. One is to have a really good algorithm. If you have a bad algorithm that doesn't do things efficiently, then you're going to get slow computations. Another is you can have a good algorithm, but you might implement it inefficiently on the computer. So another thing is you would want to write your code in such a way that it's efficiently implementing a good algorithm. And then the third thing is you'd want to have a fast computer. Okay, but just having a fast computer is not going to save you if you use a bad algorithm or you implement it inefficiently. And oftentimes, even with a not so fast computer, if you have a good algorithm and you implement it efficiently, you can often get it to go much faster than you could on the world's fastest computer. So those are things to keep in mind, and we'll be talking about sort of standard algorithms that have been developed over the years. The other point I want to make here, just with a simple example, is that we often can implement these different computations in multiple different ways. And that sort of gets at this question of what's an efficient algorithm and how do we implement it efficiently in light of the way that our computer is designed and set up. So if I think about computing just a matrix vector product, so suppose I have some n by n matrix A, and I have some vector x that I want to multiply by A. There's sort of 2 things you could do. Right? There are basically, and it basically corresponds to which is the outer for loop and which is the inner for loop of doing this calculation. Now, I can either iterate over this first, and then within that iterate over the rows, or I can iterate over the rows first, and within that iterate over the columns, and that's what the pseudocode over there indicates. But I like to think about these things sort of graphically, and so one form is take my vector x and multiply it sequentially by each of the rows. But another way to do this would be to take my first column and multiply it by x1, and then take my second column and multiply it by x2. So this is just x1, x2, etc. And multiply it this way, and it shouldn't be hard to see that I'm basically just reversing the order of the for loop, the two for loops, depending on which of these two things that I'm doing. Okay, so the next question is, suppose that I'm working in, suppose we wouldn't actually do this natively in R. We would call the linear algebra routines that are written in C or Fortran to do this. But suppose I were writing a function in R to do this computation. Which of these should I prefer and why?
I'll take the second.
Okay, why the second one?
Because R is stored data in the vector Y expression.
Okay, because R is column major, right? The same, we've had like 4 answers to questions. Yeah, so there's nothing more complicated than that. That we know that R is storing values like this. It's not going to be hard to go in and get the individual x elements, but if I do it this way, once I get x1, I can basically just the computer can basically just retrieve the whole column. That's going to be straightforward. It's going to be all sitting there contiguous in memory. When, I think I may have mentioned the cache on the computer, which is basically sort of the high-speed memory that's very close to the processor. When R goes to retrieve values from memory, it often retrieves sort of a chunk of values, and so it's probably going to it may retrieve all of these at once, and that's going to be faster than if it has to go in and retrieve this one, and then this next value over here is of course stored a long way away because of the fact that the next value after this one is in memory is actually the second one down in the column as opposed to going over in the row. So if you were to look, the linear algebra subroutines that R calls, I think, are written in Fortran. I think Fortran is column major as well. If you were to look in, Daniel's nodding his head and confirming that, thank you. If you were to look in the Fortran subroutine, you should see that if it does something like this, it is actually doing it this way as opposed to that way.
So R is column major and C is row major.
Yep.
Does it convert its memory structures between the two and call C?
No,
I see it inherently less efficient.
Yeah, that's a really good question. I should know the answer to that because every so often I wonder about exactly what happens when R calls C and what the answer to that is. And I've never actually gone and looked it up, so I don't actually know what it does. If you're writing your own C code and you pass in an R matrix to that C code, yeah, your C code is going to have to respect the fact that R is basically storing that matrix as the first column, the second column, the third column, the fourth column. So you can write your C code to respect that and to just work with that pointer of that array in C, which is what it really is in R even. But if you were actually calling a C package that would be expecting row major, then yeah, it might be that R's .call or the other functions that go out and do the C call, it might say, oh, I have a matrix, I'm sending a matrix along, I should do the transpose and send it along in the way that C is expecting. So that might very well be what happens. All right. Okay, so I want to talk about conditioning so that you guys know what that is all about. And this goes back to these numerical issues that we're seeing in Unit 7. So the idea of something being ill-conditioned is if small changes in the values that go into the computation result in large changes in the results. That's called an ill-conditioned problem or an ill-conditioned computation. And there's an important number that goes along with this, which is called the condition number of the calculation. And that basically quantifies how sensitive is the result to small perturbations in the inputs. And usually when we're talking about the condition number and ill-conditioned problems, we're usually thinking about matrix inversion or equivalently about solving some system of equations. So we have some ax equals b. We want to find x. That is a system of equations in coefficients a that are in the matrix A. We want to find the unknowns x, and we have the answer b. So you can just think of that as a system of linear equations. And so usually when we're talking about these things, we're talking about inversion or equivalently these system of equations. So let's walk through an example, and I'll switch over to R in a second. So here's the example. I'm going to try and solve this system of equations. I'm going to try and find x if I know A and I know B. This is my matrix A. This is my vector B. And if you actually just work this out mathematically, the answer is that x is just a vector of ones. So if I now go to R to look at this, what I'm going to do here is I'm going to change B a little bit, just by 0.1 for each of the values of B. So if we're just looking at that, we'd say, well, you know, we changed B by 0.1, maybe X changes by 0.1 or 0.3 or something like that. Okay, so that's sort of what our intuition might tell us. Okay, so so this is one way that in R we would solve the system of equations. We call the solve function with the A matrix and the B matrix, and that will give us back our result. And now let me suppose that what I had was that instead of somebody giving me B, they gave me the perturbed version of B, and see what the answer is if I do that. So here's X, it's 1, 1, 1. Here's the result I get if I've perturbed B. Oh my God. Right? This is nothing like 1, 1, 1, 1. Right? So I changed B by a little bit, and all of a sudden, all hell broke loose. So what's going on here? How could this possibly be the result? And I'm just going to compute the 2 norm, basically the length of the differences between the perturbed X and its X and the perturbed version and B, and basically the length of this difference vector between B and the perturbed version is only 0.2, but the length of the difference between the true X and the original X and the perturbed version of X is much, much bigger than that. Let's see. So what do I want to say here now? Okay, so let me go back to the PDF. So if we look at this and just sort of stare at it for a little bit, we're perturbing B by a little bit, and the result is that the change in X is very, very large relative to what we might have expected. So it's probably not too hard a leap to say, well, maybe there's something about this matrix A that's causing the problem, that's resulting in small changes to B translating into large changes to X, because A is sort of the only other thing that's in the problem here. So indeed that's the case. So you can do some manipulations that we're actually going to do in a slightly different variation in a second. And what you can show is that this is the perturbation in X. So this is this is the perturbation in B. So this is the length of my original B vector, the norm of that. This is the norm of, let's see, this is, what am I doing here? Make sure I've got my notation right. Right, okay, so I've defined delta B as the perturbation in B. So this says that if one works this out and gets this inequality, it says that the perturbation in X, the magnitude of the perturbation in X relative to the magnitude of the X vector is less than or equal to, yes, it's relative to the magnitude of the perturbation in the B relative to the B vector, but it's scaled by this set of terms that have to do with the matrix A. And so this multiplication of the norm of A times the norm of A inverse is the condition number with respect to inversion for these kinds of problems. So we define it as the condition of A, and that's this. And in general, we're going to work with the L2 norm, which you guys saw defined in the first few pages of the notes. And we can work out, I think I will skip it. But we can work out that this quantity is the ratio of the largest eigenvalue of A to the smallest eigenvalue of A. And so the result is, if we have that the eigenvalues of the matrix are really, really spread out, and the biggest one and the smallest one are very, very different in magnitude, then we can get this the case that this might be big, not because this is big, but because this condition number is big. And that basically says that the problem is ill-conditioned, and we have this sensitivity to the input, to changing the input vector b. Okay, so if we go back to R, yeah.
Delta B, is that the difference between B and that perturbation?
Yeah, I'm a little worried that I might have sort of thrown you off with my maybe somewhat inconsistent notation. So the delta B in the notes should be the perturbation itself, and then the perturbed version of B would be B plus delta B. And the perturbed version of X is X plus delta X. So this B perturbed should be B plus delta B, and similarly for X. So if we go back to R here, so basically what I'm trying to do here is basically in R do that equation which I just showed you, which is okay, so let's see. So we have the 16.39 and the 0.2, and if I look at, so this now here is this guy here, this ratio here. And if I look at that, we see that's 8.19. And what I'm doing here is I'm trying to do the right-hand side of this inequality. So this is an upper bound, but it's often going to be not too far off. So what am I doing here? I'm getting the ratio of the perturbed of the delta B over the norm of the delta B over the norm of B, and here I've got the biggest eigenvalue and the smallest eigenvalue of from this matrix A. And if I look at this, I see it's actually not too bad in terms of an inequality. The right-hand side is 9.94, the left-hand side is 8.20. And if we look at E in terms of the values, just to get a sense of this, we see that indeed we do have a fairly big spread in the eigenvalues. So the biggest one is 30, the smallest one is something like 4 orders of magnitude smaller than the biggest one. Okay, so questions about that? Okay, so why have we done all that? That's just sort of a mathematical anomaly, I guess, or maybe anomaly is not a good word, but that's sort of maybe not all that interesting, just from a toy problem perspective. But now let's think about what we're actually doing when we're doing computations on a computer. So what are we trying to do if we're trying to solve AX equals B on a computer? Well, we would ideally just solve that, and the computer's answer would be the same as the mathematical answer. But what we're really doing, as we know from Unit 7, is we never actually have the precise representation of any of these quantities. So what we're really doing is we're in this sort of fuzzy space where we're taking some perturbed version of the matrix A, some perturbed version of X, and that's going to be equal to some perturbed version of B. So we're basically starting with this, and we have this. We don't have the A and the B, we have the perturbed versions, and we're trying to figure out what's X. And so the goal here is to say, how big, given what we know about computer numbers and arithmetic, and information about the eigenvalues of A, how big could delta X be? How far off could we be in finding X relative to the truth?
You could avoid this entirely just by sticking to integer math, right? If you really wanted to. You can force all your numbers to be integers.
I suppose that's true, but now you're just perturbing the problem in a different way, right? You're taking your matrix and saying, I don't like your real numbers, I'm going to make some new matrix A, and you're going to find an exact solution to the problem I didn't ask you about, right? All right, I'm picking on you a little bit, but yeah. But fair question, yeah. Okay, so what do we know from what we saw in Unit 7? Roughly speaking, it shouldn't be too, I'm sort of waving my hands here, but it shouldn't be too surprising to think that the delta B over B ratio of these norms is about 10 to the minus P, where P is 16. So we've already seen that's the, basically that's the relative magnitude that we can, that we have when we're representing, the relative accuracy that we have when we're representing numbers on a computer. Okay, so basically what we can do is work out that, and I'll show you this. I might do it next time. I might do a little bit of the proof next time. But basically what we end up with is the same expression as we saw up here. And so we can say that the error in our relative error in our answer for if we try and find x to solve the system of equations ax equals b is approximately equal to, I'm just replacing the lower bound because the inequality is approximately equal to the condition number of a, which is the ratio of those biggest and smallest eigenvalues in a, times 10 to the minus p, which just comes from our inaccuracy in representing b. So one other way of thinking about that is suppose that our condition number was something like 10 to the 8th, and that would come from the ratio of the largest and smallest eigenvalues, and we know we have 10 to the minus 16. Well then what I get is I've got 10 to the minus 8, and that basically says that because this condition number is so large, I basically lost 8 digits of accuracy in doing this computation. So that's already, maybe for this particular example we'd be fine with only having 8 digits of accuracy, but as this gets bigger and bigger, we basically are losing more and more digits of accuracy, and so we could get something where we basically cannot numerically estimate the thing that we want to estimate with any accuracy at all. Basically the error might be the same order of magnitude as the actual vector itself, the vector x itself, in which case we haven't really solved the problem at all. And that would be the case if our condition number were really bad. So I think, given the time, I will show you a bit of that proof next time. What I want to show you before we finish up here is just how this can actually, that we see this actually rising in practice. And in a lot of cases, including the one that I'll show you here, it's actually not a hard problem to solve with a few tricks. So here's the idea. Suppose that suppose I have some data and I'm running a regression where I have some data that are over time. And on the x-axis I have the time that I'm looking at is between 1990 and 2010, and I have some data, whatever y is. And I think about this problem, and maybe I look at the data and I say, you know what, this looks sort of quadratic. I should put a quadratic term in to account for the curvature in this regression. I don't want to just fit a linear regression. Well, okay, so I'm going to go ahead and do that, but I'm going to do it with different versions of. So x here is just going to be the vector 1990 to 2010, and that would be my first. That's my first variant on constructing the x vector. Another thing I might do is I might center all of my values and subtract 2000 off from all of the x values. So the x values are 1990. My x vector is 1990 up to 2010. Maybe I should mean center this x vector and subtract 2000 off of all of these values. And another thing I could do is I could center it and then scale it so the standard deviation was around 1. Okay, so I could either center or scale or do both of these. And if I do, so what is x capital 1? Sorry, my notation here, I probably should have made this a little bit nicer. So this is just constructing a design matrix, a covariate matrix, where I have a vector for the first column is the intercept, the next one is the 1990 to 2010 or the variations on that, and the next one is the quadratic term where I've squared the second vector. Okay? So that's all I'm doing here. Except I'm doing it for these 3 different variations, for the original x, for the centered one, and for the centered and scaled one. And now I'm going to go ahead, I've now got my x matrix. Well, what do we need to do when we run a regression? We need to solve the system of equations x transpose x beta equals x transpose y. So this is b, this is a, and this is x. So this is the x I'm trying to find, just to put it in the notation we've been seeing. So I'm going to take the cross product of x1, which is just computing this, and what I'm trying to do here, at least mathematically, is do x transpose x inverse x transpose y, and hope that the result that I get out is represented with a fair amount of accuracy. I haven't lost a ton of accuracy in representing my regression coefficients. So let's go ahead and look at the eigenvalues from E1. It's awful, right? This is 3 times 10 to the 14th, and this is minus 3 times 10 to the minus 8. So the condition number here is something like 10 to the 22nd. Okay. So if I tried to then go ahead and compute beta based on this, I don't know if I actually have the code in here to do that. Maybe not. You could play around with it on your own if you wanted to. What we should see is that the beta hat that we get out is totally inaccurate as a reflection of the true beta hat. But if I do the simple thing where I just center all of the time values and subtract off 2000, that's already helped a lot. Now my condition number is basically about 10 to the 4th, something like that here. Or I guess 10 to the 3rd, I guess. So that's not too bad, right? If going back to this idea of how many digits of precision do we lose, if this is 10 to the 3rd or 10 to the 4th, I'm not losing too many in doing the calculation. And if I actually do the centering and the scaling, things are actually quite good. Now it's basically, the condition number is basically 10. Right? So you're losing 1 digit of accuracy in doing the computation. So that's just an illustration. You guys, I think, have probably seen in other contexts, somebody might center something or might do some scaling before doing a computation. There are other examples of where making sure the magnitude of the numbers are not too big, and not too different from each other are helpful. But this is one example of where it's helpful, is in doing these kinds of problems. That it's often good to work with numbers that are magnitude around 1 or so, and where their variability is something like it's around 1 as well. So we're not working with numbers that are really tiny, and we're not working with numbers that are really huge. And that was, this was a case where, if I take 1990 and square it, it's sort of a big number, but it's not that big a number, right? But it makes a huge difference in this case. And part of the reason is I'm taking all of these values and I'm squaring them, and then I'm passing them through all the calculations that we're going to see for doing matrix factorizations, and all of those numbers are going to start adding together and potentially being multiplied by each other, and so the numbers can get much bigger as well. Okay, so let's quit there. I will show you a little bit of the proof of how this is derived next time, and then we will start talking about solving systems of linear equations and starting to get into matrix factorizations.